Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Gaspard Duchene, who's come to us from UC Berkeley this morning. And Gaspard did his BA in physics at the University of Grenoble, where he also did a master's in astrophysics and a PhD in astrophysics, looking at young binary stars and their environments. He then came across to the US for a postdoc at UCLA and went back to France to the Observatoire de Grenoble for an associate astronomer position, and then came back in 2007 to UC Berkeley, where he now is a assistant researcher, astronomer, and lecturer there. Gaspard's interests revolve around star and planet formation, stellar multiplicity, which we're going to hear about today, and protoplanetary disks and debris disks. And he's also interested in techniques of high-resolution techniques such as adaptive optics, and interested in imaging, photometry, polarimetry, and spectroscopy of and how they relate to astronomical observations. He's also interested in radiative transfer modeling of debris disks. So today he's going to talk to us about recent surveys and how they shine light on planet formation and linkages with possible linkages with stellar multiplicity. So if you'll join me in welcoming Gaspard.
Yeah, is that on? It's on? All right. So thanks for coming, everybody. As Adrienne has mentioned, I have, for quite a while, been interested in stellar multiplicity on one hand, and protoplanetary disks and debris disks and planet formation on the other hand. And so that drives naturally to the topic of the talk I'm going to give today on planet formation in multiple systems. There's been a long-standing history of research on planet formation in general, usually around a single star, and we sort of have some ideas about how that might work. There's a very long-standing field in astronomy of looking for stellar multiple systems, binaries and others. It's several centuries long. But the merging of these two, or the collision between these two fields, is not necessarily always very thoroughly searched. And over the few years, I've been interested in that convergence of topics. And I started thinking about this whole theme 3 years ago at the IAU General Assembly in Rio de Janeiro, where I gave a talk on a similar topic. And I was highlighting some interesting trends that some of them I'm going to show again today. And since then, the biggest changes that provided even more information came mostly from the Herschel Space Observatory, far infrared telescope, which has conducted a number of key projects, large-scale projects, two of which I'm involved in, GASPS and debris, and I'll talk about those two later on. And they're bringing some very interesting new light on this topic. And there's also some interesting highlights from Kepler that I'll briefly talk about in a minute about planets and binaries or multiple systems. So let's start with the basics. Planets and multiple systems. That's an odd question. Why do we care? Obviously, science fiction had thought about this for a very long time, many decades. So if science fiction had thought about it, then very definitely they must exist. So that is a fact. Right? Okay, that's a start. Let's move on from science fiction into science. And in fact, this is no longer a question mark. It's now been a little while that we know that planets do exist in multiple systems. In fact, one of the very first planets discovered around pulsars, with all the caveats about those type of planets, was found in a circumbinary system. Only a couple of years after the first Royal Velocity planets, 51 Peg, came out another planet that was found in a binary system as well. So it was very early on that was known. That's 15 years ago. And now with Kepler, and I'm highlighting here in the bottom right, the sort of PR picture of Kepler 16 of a circumbinary planet, where you have two normal main sequence stars orbiting each other, and further out a planet, a Jovian-type planet. And there's now two more, Kepler 34 and 35, that are in a similar type of configurations. So planets in multiple systems, this is not even a question anymore. They do exist in multiple systems. The answer to that question is an emphatic yes. That is not a question at this point. What is more interesting is that they do exist in a very remarkable diversity of systems. Not all the systems are all the same. There's, just like planets around single stars, you can see planets in binary systems of very different types in terms of where the planet is relative to the two stars, or more than two stars if they are there. So going into a little more detail, some questions that then become natural to ask is, after all, does a stellar companion, the presence of a second star around that first star forming planets, makes any difference at all? And if so, what are the differences? What is different in the planetary systems and binary stars? Is it in their properties or in the initial conditions? How does planet formation start? Or does it go about? Do they go through different processes? And these are the type of questions that now we can start to answer, or at least give some insight on. And the main goal of my talk today is going to be to summarize for you a number of empirical studies that shine some light onto these questions. I'm not going to answer all of them, because obviously as the entire topic of planet formation, we don't have answers for everything, but at least we start to have a better view of what's going on from the empirical standpoint. So before I do that, let me just briefly pose the schematics of the problem. So what we think we understand about planet formation is that they form in some form of circumstellar disk around the star, early on in the stage of the stellar life, within a few million years, maybe a few tens of million years. The exact details we don't quite know, and I'm not going to talk too much about that today. Certainly it goes from taking some very small dust grains and aggregating them together into forming something larger and larger until gas can be accreted to form giant planets. I'm not going to talk more about the details, but that's the general picture. Now, back into the context of today's talk, what is the influence of a stellar companion? If you put a second star in that system pretty close by, what's going to happen? Now, the first thing, the most simple thing that you can think of is what we call dynamical truncation. This second star, because now you have two stars, any particle in the disk feels more than just one central force, so it's a three-body problem in essence. And there's a lot of tidal forces that get impinged onto the material of the gas, and the basic outcome of that is going to be disk truncation. The parts of the disk that are too far out from a star and too close to the other star will be in unstable orbit. They won't be able to stay there for a very long time. So the disk is essentially going to be truncated, and only the inner parts are going to be sufficiently strongly bound to one star that they won't be disturbed too much by the presence of the companion. Okay, so we're going to have dynamical truncation. That's, again, a very long-standing known dynamical problem. But then what? What happens then for planet formation? Does it still go the same process? Does it stop at all because truncation somehow prevents everything? That is the type of open questions we have to answer. Like I said at the beginning, we do know planets will form, so we're going to have to find a way to do that. But will it go through the same processes as a normal star with just one disk and no other star around it, or will it go through different processes? And this is what we're going to talk about today. So putting some numbers into the context so we know what we're talking about here, let's go back to stellar multiplicity. Focusing for a moment, and actually for most of the talk, I'm going to talk about solar-type stars because that's where a lot, if not most of the planets we know around other stars are located. About half of all solar-type stars have a stellar companion. Okay, so that's a pretty large number. It means the sun is, borderline in the majority or the minority, depending on the statistics. We're not going to make a claim here. But that's a significant number. Most importantly, it's not just the number, it's where are these companions relative to that star. They are distributed in a very broad range of separations, or orbital periods. Some stars are as close as a few days orbit, like much inside of Mercury's orbit, but some of them are tens of thousands of AU away from the primary stars. That's a very broad range of separations, which is illustrated in this plot here, which shows the distribution of separation for all known solar-type stars in a volume-limited survey around the sun. And the top axis shows you the separation in astronomical unit. And you cannot read off the numbers because they're very small, but they go from 10 to the minus 2 to 10 to the 5 are the two numbers on the left and the right. So that's 7 orders of magnitude in separation. That's a lot. Now, if you break it down a little more, you realize that if you put a vertical line at about 100 AU, most companions are in this type of orbits, within 100 AU of the primary star. Now, you have a star, and a second star, it's somewhere between 100 AU. That's about 2/3 of all the binaries we see in the field. And even worse, if you look at very young stars, pre-main sequence stars, when they're presumably forming planets, the frequency of companions is even higher. So the problem is even worse. It's an even higher proportion of companions that we might have to deal with to form planets. So by any means, this is far from a marginal phenomenon. This is more like the standard process. A lot, if not most of the stars that are trying to form planets at least, are going to be in a binary system. Maybe not all that succeed, maybe not the majority of those who succeed, but at least those who try at the beginning, who have a chance to try to form planets. Now I put this cutoff at 100 AU here for a reason. If we image protoplanetary disks, so when they're very young, million years, still gas-rich, no planets presumably are formed yet, and we try to measure their size, we can draw histograms, a distribution of the size of these disks. And again, we have a fairly broad distribution, but the typical size is 1 to 200 AU. So remember, I told you within 100 AU, you have like the majority of the companions. You have 2/3 of the binaries are within that radius. So essentially, that companion is smack in the middle of the disk or just at the edge of that protoplanetary disk. Obviously, that's not stable. The disk isn't going to be truncated. But that means that this interaction between disks and planets is presumably pretty important. Disks and companion, a stellar companion. Now, like I said at the beginning, the first thing that this stellar companion will do is truncate the disk. It's going to make it smaller. Say if it's a 100 AU binary, it's going to make the disk maybe 30 AU, something like that. Depends a little bit on the parameters. 30 AU is still pretty large, and certainly it's larger than what we think the region of planet formation is. We generally think it's somewhere between a few AU, and maybe 10 AU or something like that. So you might think truncation is not that important after all, because it's getting rid of what's outside. So, oh well. Now the key thing here to keep in mind is that this inner 10 AU, or 20 AU, whatever you want to call it, only contains a very small fraction of the total mass of the disk when it's young. If you take a protoplanetary disk, just when it formed, 90% of the mass is outside of 10 AU. Now if you're truncating that out, then you're getting rid of all the mass. And now you're going to not have any mass anymore to form planets, or at least not Jovian-type planets. Maybe Earth-like planets, but certainly not Jovian mass planets. So it is still important to keep in mind that truncation as a factor, because of this outer mass reservoir that is typically sitting for a long time at 100 or 200 AU away from the star, and that's just gradually, through viscosity, accrete towards the center and help form planets. So truncation might be a very important factor here. The interaction with the companion could potentially have a very drastic effect on planet formation. All right, so that was for setting the context. Now I'm going to jump into the core of this talk, and I'm going to divide it into 3 different blocks. I'm going to tell you about what we know about the relationship between multiple star systems and protoplanetary disks, so the initial conditions of planet formation. Then I'm going to jump into multiple stars and debris disks. So debris disks are disks made of planetesimals, rocky bodies, lots of them, not necessarily planetary systems, but something like a very early solar system after the gas is removed. And then I'll finish with a discussion of multiple stars and exoplanet systems as we know them. And compare, and at the end of the talk, I'm going to try to put these 3 topics together and try to draw a bigger picture as to what we've learned in the process. So let's start with protoplanetary disk, very young, million years old or something like that, gas-rich. If you look at binaries at that age, when there is a disk in the system, usually there are 2. If there are 2 stars, both of them have a disk. It's not like you get 1 star with a disk and 1 star with no disk. In most cases, both of them have a disk. That's good news. That means 2 stars can form a planet potentially. If you go into a little more detail and you look at how big are the disks around the higher mass primary and lower mass secondary, you can try to image those systems. This has been done here by a group of Harris et al. At the SMA, and they're mapping a number of known young binaries and trying to see where is the dust as they can probe it into the sub-millimeter continuum. They find that typically the disks around the primary star, the more massive star, the disks are more massive themselves, and they tend to survive a little longer. Okay, and what I mean by this second statement is that if you find a binary with only 1 disk, it's usually the more massive star that is disk left over, and not the least massive star. So the least massive star lose their disk faster. Okay, so if you put that together, the intuitive outcome of that is that the primary star, the more massive component, offers the better grounds to form planets because it has more mass in its disk and it's going to last longer. It's going to stay there longer, so presumably it has more time to form actual planets. Okay, so we might expect planets to be more frequent around primary star than secondary star in binaries, and we'll get back to that later in the talk. Now going into a little more detail and looking at what is the importance of the separation of the binary. how much of a difference does it make if the companion is close or far away? It turns out it does make a big difference. And this survey here using some Spitzer data by Adam Krauss recently looked at taking a number of binaries in the Taurus young star forming region, very nominal place to look at for pre-planet formation phase. And it looked at all these binaries as a function of separation, which is plotted on the bottom axis. On the left are close binaries, on the right are wide binaries. And it just measured what's the proportion of these binaries that has a disk. And as you can see in this plot, the close binaries have much less disk, much less frequently a disk, than the wide binaries. Now the blue swath in the horizontal line at about 80% is what is measured in the single stars. The stars actually don't have any companion at all. So it's sort of a reference standpoint. And you can see that the wide binaries, and by wide here we mean larger than something like 50 AU, something like that, they have a disk just as frequently as single stars. As if the presence of a companion doesn't prevent the formation and long-lived presence of a disk. On the other hand, the close binaries, they only have not even half of that. The frequency is increased by a factor of 2 to 3. So in binaries tighter than 50 AU, the probability that the disk can survive for a while is pretty low. It's not zero, but it's much lower for sure. The actual physical phenomenon explaining that is not entirely clear. Because of the way these observations are made using Spitzer near-infrared continuum, you're essentially probing the very inner regions of the disk. And so you don't really are sensitive to anything like truncation, which gets rid of the further out, colder material that Spitzer that cannot even detect. So it is not a matter of just truncation. It could have to do with the disk never forming at all in the tight binaries, somehow because of the two seeds of protostars swirling around them in this cocoon of gas and dust, just never lets all the material fall into a disk. Could be. It could be that the disk just dissipates faster or disappears faster. It forms, but doesn't last not even for a million years, maybe just a few hundred thousand years or something like that, instead of several million years. That is not quite clear. My suspicion is that this fast dissipation somehow is more relevant, but it is not, let's say, a concluded question at this point, I think. Sure.
Do they resolve the star system with Spitzer? Or this is an integrated flux?
That is with integrated fluxes for all binaries in this plot. Is that a correct statement? Yes, it is. At the distance of Taurus, with Spitzer, at the wavelengths they're working, you cannot resolve any binary closer than 600 or 700 AU or something like that, which is further to the right. So it is a total. Let me rephrase. This observation shows that at least one star has a disk. That is what is counted here. As I said at the beginning, from other observations from the ground, higher resolution, we can tell that usually when a star has a disk, the other component also has a disk. But that's a separate statement not made on the same observations. Now, interestingly though, although these disks in closed binaries are much less frequent by a very significant fraction, they do survive very long. If you do the same study on an older star-forming region, you will realize that the fraction of disk has not declined any longer. So those disks that are in here, those only 20, 30% or something like that of the closed binaries that have disks, those disks will actually live as long as the other ones, some 5 million years, give or take a few million years. So they're not going to have a shorter lifetime. It rather looks like some disks just get dissipated, cleared, destroyed, whatever you want to call it, we don't quite know, very shortly, within the first million years, before we can even see them. But those that manage to survive that first phase actually will last for several million years. So again, they might be able to form planets. So that's just for the presence of a disk. Let's move on now to more detailed properties of this disk. And the first one we might be interested in is the total disk mass. Is there enough material to form planets in the first place? Good enough to have a disk, but doesn't tell us the whole picture here. So recently, this Harris et al. Study I described earlier already, using the SMA, has refined a trend that was known for a long time now, for 15 years or so, and that is illustrated in this plot out that I'm showing here, which shows the total submillimeter flux you receive from a disk, and that is assumed to be proportional to the total disk mass, okay, as a function of the separation of the binary. So again, closed binaries on the left, wide binaries on the right, and the black points at the very right of the figure are the single stars. And what you can see pretty readily is that there is a very sharp decline of the flux as you move towards white binaries, single stars to white binaries to closer and closer binaries. There's much and much and much less dust left over in these tight binaries. It is not entirely clear whether that means the disks are really less massive or whether there are particularly thick effects, but leaving that aside, there is definitely something happening to the outer reservoir of the dust in the closer binaries. And that is very naturally interpreted as an effect of the truncation. You've removed most of that dust in the first place, or at least you've compactified it into such a small thing that it doesn't emit much in the sub-millimeter. So it's very well understandable. One interesting thing to see in this plot, though, are these 4 outliers right up here. Oops, jumped one more. No, that's good. That are in purple up here in the top left. So these are closed binaries with very large sub-millimeter flux, meaning very large disk masses. So they're like closed binaries, very high disk mass, which is opposite to the main trend. Turns out those 4 guys are all circumbinary disks. You have 2 stars, and the material is around that binary, not around either of the 2 stars. So they're a different category altogether. We're not talking about a circumstellar disk, we're talking about a circumbinary disk. Doesn't mean it cannot form planets, but at least it's a different category. That's why they're shown in a different color and put on the side, let's say, before looking at the main trend. On the other hand, something that was of interest at some point, people wondered whether the mass ratio of the binary, the ratio of the masses of the 2 components, made a big difference. Dynamically speaking, people don't expect a huge difference. It does make a difference, but it's sort of a second order effect. And in fact, as shown in the second plot here, again, sub-millimeter flux on the y-axis and mass ratio from 0 to 1 on the horizontal axis. And there's very little trend into it. There's a mild trend, but it's barely significant. So essentially, once you have a companion, a stellar companion, it has an effect, and that's it. It doesn't really matter if it's a 0.1 solar mass companion, a 0.5 solar mass companion. It just has about the same effect. All right, so that's for the total disk mass. If we want to look at other parts of the disk or other properties of the disk, we might be interested into what's happening into the inner regions where we think planets are going to form. Is there any evidence that something different is happening? And the way to do that for a long time was to look into Spitzer data using near to mid-infrared data that try to, in different criterions, to probe the structure, the geometry of these disks. And there are 2 trends shown here, one about the 10 micron silicate feature and one about the general near-infrared colors. They both tell us something different. One is about the size of the grains, one is about the geometry of the grains. The main point I want to make out of these 2 plots is that the red and blue are showing distributions of points or histograms, show you the difference between the binaries and the single stars. And the outshot of it is that there's essentially no difference. Can hardly tell them apart. So these regions that are probed by the Spitzer data are essentially totally unaffected by the presence of a stellar companion, as far as we can tell. Now, one very big caveat here is that these 2 probes here are very sensitive to only the surface of the disk, the upper surface of the disk, within the first AU from the star. That is the one region these 2 plots are probing. So this region within 1 AU of the central star is unaffected by the presence of a stellar companion. But if that stellar companion is 10, 20, 50, 100 AU away, that might not be such a big surprise that there's not much of a difference in the first place. And it's even more so because of the optical thickness of the disk. We're only probing the surface. So we don't even know what's happening really in the midplane where planets might form because we cannot see that region. We only see the surface out of it. So we have to extrapolate downwards to figure out what's going on. Still, at least it seems the binaries are not dramatically affecting the disks in the inner regions. That's good. But there are still some missing pieces in this picture. And the main missing picture up to now is the actual region where planets actually form. As I said at the beginning, although there are debates exactly, and we don't quite know exactly where planets form, we think they form within a few AU. Some people will say about 3 AU, some people will say 5, 10, 2, give or take. We could make a poll here, but it doesn't really matter. That region is a little bit further out than what Spitzer can probe. And this is what is shown in this plot here that shows the cumulative flux that comes out of a disk as a function of radius. So let me explain that. On the left-hand side, you have 0.1 AU. On the right-hand side, you have like a few hundred AU, and that's for a typical Titari star, solar mass Titari star. And this, each of these curves is showing you, if you make a circle around on top of the disk and you measure how much emission is coming out of this circle, and you make that circle larger and larger, you get more and more flux, and that is the curve going out from 0 to unity. It's normalized to unity, okay? And each of these curves is made for a different wavelength. On the top left is 10 micron, and shorter wavelengths will be even further up on the left here, and that's typically what Spitzer probes. And you can see that 90% of the emission that Spitzer can detect is coming from the inner 0.1, 0.2, a quarter of an AU, something like that. Like I said, these regions this is only what we're probing with Spitzer. It's interesting, but that's the only region we're probing. If you look at the SMA, the studies I was showing before about the dust mass, it's the curve all the way to the right. And this one, 90% of the flux is coming from outside of 20 AU. It's the cold outer material, outer region, where we're eventually going to get, say, the Kuiper belt in our solar system. That's interesting too, but that's a different picture. The planet-forming region is probably somewhere in that green swath I draw in the middle, and it's best intercepted by this curve here at 70 micron, meaning that's the region you want to go, the wavelengths you want to go if you want to probe that planet-forming region. Unfortunately, that is not easy to do. Spitzer could go that far out, but it was difficult. Sensitivity was limited, confusion was an issue, all sorts of instrumental problems. So that's a big of a problem. Now, the other big problem I haven't even talked about yet is that all of those probes I've talked and I mentioned so far, Spitzer, SMA, they only talk about the dust. Obviously, we care about the dust because to form planets, we'll need that dust. We need rocky objects. But most of the mass, something like 99%, is in the gas in the first place in these protoplanetary disks. And we don't know anything about that gas if we only look at this continuum. So we need to probe that gas. And again, we need to probe that gas, hopefully, ideally within this planet-forming region, ideally even better everywhere, but it's very difficult to get probes that will go into that region. So that's where Herschel comes into the equation. Because Herschel is a far-infrared observatory. It goes from 70 micron all the way to 500 micron. Exactly the right range you want to do that kind of stuff, to study that region. And one of the big projects that was granted time on Herschel was called GASPS. And I had a blank coming on the road. I was trying to remember what GASPS stand for. I think it is gas in protoplanetary disks in some form. I'm not quite sure what the final S comes from. But anyway, that project targeted about 250 young stars. And by young, I mean anything younger than 30 million years. Including about 100 in Taurus. So again, that's the prototypical region we like to look at. That's very nice, close, convenient. We can also see it from the ground very nicely. And we've looked at that many sources. And obviously, if you pick 100 stars in Taurus, a lot of them are going to be binaries. So you can start to play similar games as the ones I've just shown before that we did before with Spitzer SMA, but now with the Herschel data and see what happens. So before I show you Herschel result, let me show you what happens if I take just the sample that we've observed within GASPS in Taurus, so some hundred-something objects, and I don't remember the exact binary fraction in that subsample, but it has to be that there are something like 50 binaries or something like that. And this is just a plot of the submillimeter flux versus separation. So this is not Herschel data. This is again submillimeter flux. So it's very similar to the plot we've seen before from the Harris et al. Paper, especially if I highlight for you the two circumbinary disks out there. And if you mentally flag those out, you will see the usual decline of flux as we go towards closer and closer binaries. Okay, so nothing new here. That's the same sample as before, so it's not a big surprise we find the same result. But now let me draw some similar plots, not with the submillimeter flux, but with the Herschel fluxes. And I will draw you one with a continuum flux, so the dust emission, and one with an emission line, the oxygen 1 forbidden transition at 63 micron, which is one of the main line cooling the main cooling line for the gas, so it's very bright and fairly easy to pick up in disks. And if I draw the same plots with a function of separation on the same binaries, this is what I get, where the red and blue are showing you the continuum and the lines, and the basic point is that there's no trend. It's just flat. Well, there's a huge scatter, of course, because from object to object, you get different disk geometries and different exact cooling processes depending on all sorts of phenomena like UV flux and X-rays and so on. But the basic thing is that there's no dependency at all on separation. And remember, those two probes, certainly the continuum, but even the O1 line, are essentially probing the planet-forming region, a few AU from the star. Now, further out than Spitzer did before, but not nearly as far out as the SMA was doing as well. So from looking at that, you might conclude, at least at the zeroth order, that the stellar companion has a very small, if not no, influence on these regions. There are still some caveats. Those regions are still optically thick, meaning you don't see the actual midplane where the planets are forming. You're seeing the surface high up above the middle of the disk. So it could be that things are still different in the middle and you can't see it. But at least in the surface, the disks just look just the same. If there's a close companion, if there's a wide companion, or there's no companion whatsoever. So it might be that companions don't do so much damage as we might have thought for a while. All right. So let me summarize what we've learned here about protoplanetary disks. First of all, disks around primaries, more massive components, are more auspicious to planet formation than those around secondaries. All right. The outer disks, anything outside of 20, 30, 40 AU, are severely depleted when there is a companion, especially if that companion is within, say, 100 AU or something like that. That's not a big surprise. That's just dynamical truncation. It might indicate, it probably indicate that tight binaries have lower total disk masses, although that remains to be seen exactly. There's also evidence that those disks are also shorter lived, or at least some of them are very short lived in these closed binaries, a very large fraction. And on the other hand, if you look at the planet forming region, and by that I mean the region a few AU to 10 to 20 AU away from the central star, appear to be unaffected by the presence of a companion, as far as we can tell, using the probes we have with Herschel or with Spitzer. It might not be the final picture, but that's as far as we can get. All right, so let me move on now and go into the second phase. Later on, now we're going to talk about multiple stars and debris disks. So now in debris disks, the gas is gone. So gas giants have to be formed if they are there, because there's no gas left anymore, so that's it. Terrestrial rocky planets may or may not have formed yet. It's not clear. What we see in the debris phase is very small dust resulting from collisions of a number of solid bodies, planetesimals. So the planet formation process has gone to at least the step of forming planetesimals. Whether or not it will or has gone to terrestrial planet formation isn't clear, and whether or not Jovian planets are present is very hard to tell because of sensitivity issues. So what do we know about debris disk and binaries? Well, there's been a lot of studies. Again, this is not a new field, especially with Spitzer over the last few years, has looked at a number of samples specifically for binaries or specifically for debris disk and binaries or for binaries and debris disk. You can make your way around in many ways. And the results are fairly confusing. There are some statements saying that, well, the top one is maybe the one to remember for now, that the binary fraction among debris disk system is on the order of 15 to 25%. Okay, that's lower than what we see in normal field stars. So it seems like in binaries there are less disks. However, the binary surveys are largely incomplete, especially for A stars. It's very difficult to find a very 0.1 solar mass right next to a very bright A star. So whether or not that is complete is not clear. Some people have claimed that binaries tend to lead to less debris disk emission, and some people have said that if anything, then the fraction of binaries is actually higher than among single stars. So it's very, very different conclusions were drawn from different samples, presumably in part because of the various biases that go into these studies and selection effects, let's say. And I would argue that the situation definitely needs some clarification here. Very recently, before we get into Herschel, David Rodriguez at UCLA with Ben Zuckerman has been looking at a pretty large sample of over 100 known debris disks from the IRAS and ISO epoch. So pretty much all of these guys that add an infrared excess from IRAS or ISO is looked at, typically A through K type stars, and is looked very thoroughly for companions of all sorts. Spectroscopic binaries, visual binaries, common proper motion binaries, any type of separation. And is tried to be as complete as he could. And the outcome of his study is the histogram on the left, which shows the range of separation, the distribution of separation of companions he found. And it's sort of flattish. There's obviously not very good statistics. There's only so many binaries in there. But the fact that it's flat is actually meaningful, because what you expect for field stars is some form of a peak somewhere in the middle, which is shown by the dashed Gaussian distribution in the middle. So it seems like in the middle there is a deficit of binaries in this plot. And so the way you can envision that, think about that, is on the left-hand side you have very short period, very close binaries, and then you have a second binary debris disk. So you have two stars orbiting each other and the debris disk is somewhere further out. Or vice versa, at the very right of that plot, you have very wide binaries, and now it's one of the component that has the debris disk itself. And the one in the middle, typically with separations of a few to 50 or maybe 100 AU, are pretty rarely have debris disks, much less than you would expect from normal single stars. So it sounded like binaries, companions, the presence of a companion, especially in that sort of 1 to 100 AU range, is somewhat disruptive to the debris disk phenomenon. It is still unclear whether there are selection biases in this because of the way the IRAS and ISO survey were conducted. And so it is not necessarily the final answer. And the best way to address that issue is actually to conduct not a complete survey from the IRAS catalog, but which is nice, but to go a step beyond and do a properly volume-limited survey, ideally unbiased in some form. So you look at as many stars as you can within a certain distance of the sun, and you look at all of them in the same way. And you don't make any selection criterion as to whether it's a binary, it's a young and an old star, and so on and so forth. And that is exactly what we've done, again using Herschel, this time in a project called Debris, and that I won't even tell you what it stands for because it's very long and I'm going to not get it right, but it's obviously searching for debris disks. And in that survey, we've looked at about 450 targets. Spectral types A through M, A, F, G, K, and M, about 90 of each, and it's essentially the closest 90 from the sun. There's a few rejections because of confusion in the sky and brightness at the far infrared wavelength, but that's the only criterion that went into the sample definition. So it is an unbiased volume-limited survey, and with a very uniform strategy. The histogram on the right here just shows you the distribution of effective temperature, and you can see we've sampled everything from the pretty cool mid to late M-type stars that are very close to the sun, all the way to A-type stars out to 45 parsec or so. So that survey gives us a pretty complete view of the occurrence of debris disks around stars as a function of spectral type. And if we get information about multiplicity, then we can do the same games of looking for trends with multiplicity, again in an unbiased way. So to do that, we have looked very thoroughly into a number of catalogs, and we're still trying to input a few more into our search, but we're pretty much complete at this point. And most importantly, we've conducted an extensive survey at Lick using the adaptive optics system up there to search for extra companions that people might have missed. You would be surprised how many companions are still not known around bright nearby stars. There's all sorts of stars people never looked at. And there's even many more that people have looked at, found something or didn't find something, but they were not interested and didn't say anything about it anywhere in any paper. So you still have to go back at it and do it yourself, because not all the data is in the archive, unfortunately. We found a few, as the one indicated here, companions that were not known before we did our survey. So they're candidate at this point. We still have to confirm their companionship, that they're physically bound to the primary stars, as you can see in these images. But we do find more.
Is it still in the Taurus region?
No, now we're talking about main sequence stars within a few, for M stars out to 8 parsec of the sun, and for A-type stars out to 45 parsec or so. So their main sequence, giga years old. We don't really have very good estimates of the ages. It's much harder than the main sequence. All right, so now we're equipped. We have a volume-limited survey, unbiased. We know everything about the debris disk, presumably from the Herschel observations. We are supposed to know everything about their companions from this survey here. What do we find? Well, the first result is that unambiguously, debris disks are less frequent in binary stars. And that is across the board as a function of spectral type. The histograms down here show you the frequency of debris disks as a function of spectral type, where the red histograms are for multiple systems and the blue are for single stars. And although the uncertainties, the individual uncertainties are somewhat large at this point, and you cannot really tell the difference, statistically speaking, between the A-type multiples and the A-type singles, nor can you for the F, for the G, for the K and M. If you put them all together, the effect becomes very significant. And the difference is almost a factor of 2. That's something like 14% of binaries have a debris disk, whereas 23% of the single stars have a debris disk. That's a pretty significant difference. So very clearly, when there is a companion, something happens. Debris disks don't form nearly as much. Planetesimals don't form nearly as efficiently. If you go one step further and you worry about this distribution of separations, remember I told you there was some hint that the debris disk, this sort of intermediate separation range was the one that was very disruptive. We can look at that as well in this survey. Now we have enough companions to draw these histograms. And this is the histogram of separations for all the companions we have in our survey. And the blue histogram is for all the systems that don't have a debris disk. So it's sort of a control sample. It's all the nearby binaries, essentially, over the entire A, F, G, K, and M stars spectral types. And the red histogram that is shown at the bottom is the same separation of this distribution of separations for the systems that have a debris disk. And you can see this familiar flattish structure we saw in the Rodriguez et al. Paper before, but now it's slightly higher significance. And most importantly, we have a control sample that is defined in the exact same way. It is the same volume limited, the same Herschel data. We're sensitive equally to debris disks, and we're sensitive equally to companions. So we can make a one-to-one comparison. We know what to compare to. And now I've drawn for your eyes these two vertical lines at something like 1 and 1,000 AU to show you that outside of this regime, then the difference is not very significant. Debris disks occur roughly the same frequency outside of these two bars, but in the middle, there's a very clear deficit. So the presence of a companion within 1 to 1,000 AU definitely decreases the frequency of debris disk. by quite a bit, by a factor of 3 or 4. And that accounts for the overall decrease from 14 to 23% of debris disks. All right. I think we're just perfect on timing. So let's move on to the third topic now and talk about multiple stars and exoplanets and what we know about them. So I've already talked about a few highlights at the very beginning, so individual systems. As you've guessed by now, I'm sure, I'm more interested into the statistics and the main trends, so that's what I'm going to focus on. Before I move on to some plots here, let me just say something about the fact that, not surprisingly at this point, I would expect, we find that most planets that we know about, exoplanets that are in binary systems, are found around primaries. Remember, their disks and the primaries are more massive, they're more prone to planet formation, which is nice. So it sort of makes sense, except that very few searches have been made around the lower mass components. So actually, it's just a selection bias. So whether or not that effect is real, it's not clear. There are exceptions, as I mentioned here. There are a handful of planets in triple systems, so even having 3 stars is not much more disruptive than 2, apparently, or at least planet formation can occur in such systems. And there are some pretty extreme cases. One of them, long studied now, is called gamma sep. And in this plot here that shows the separation of where is the planet and where is the stellar companion relative to the star. So the left symbol, the open circles, are where are the planets, and the right stars, the stars to the right, are where are the companions, and vertically is just a sequential number of binaries. I've highlighted in red this gamma sep system, where the planet is orbiting at 2 AU from its star, and there's a stellar companion that's only at 20 AU. That's not quite very far away. So that has been a very interesting system for dynamicists who want to know whether that's long-term stable. Can it live for billions of years? Turns out it apparently can, as far as I know, unless there are some new studies I'm not aware of. But there are systems that are pretty extreme like those. Okay, so back to the statistics now. What do we know? First of all, we know that at least a third or something like that of exoplanet hosts are in binary systems. So, like I said, it's not just a side effect of 1 or 2 binaries out there. That's a fairly substantial number. It is somewhat less than what we see the frequency of planets into single stars, but it's not that bad. And, like I said before, there are severe negative selection effects. Binaries are very annoying for those people that are looking for companions, more than helpful in most cases. And so they tend to, oh, that's a binary, I'm not even looking at it. And so if we know that already a third of the stars that people looked at actually are binaries, it might even be more than that if they had not made that selections in the first place. There is marginal evidence that companions that are too close are actually disruptive of planet formation. And this somewhat complicated plot over here shows you the difference of the binary frequency between systems that have a planet and systems that don't have a planet. And the main outshot of that is that left of the bar, of the vertical bar, within 100 AU, companions are much less frequent. So if you have, or planets are much less frequent, depending on which way you want to look at it. In other words, if you have a stellar companion within 100 AU or less, you're less likely to have a planet. If you have a companion that's further away than 100 AU, you're equally likely as a single star to have a planet. We can expect better statistics out of Kepler. I'm sure that people are studying into that. I'm not part of the Kepler team, so I can't really tell. It's a little difficult because a lot of the Kepler targets are far away, so it's hard to find the binaries in them. But still, it's something worth looking into. More interesting trend came out when I was starting first to prepare that talk about some peculiar trend that was first proposed quite a while ago now, back in the days when there was only maybe 100 or 150 planets known, so it was kind of a small number. And people start to look at anything that could differ between binaries and single. And Zucker and Mazzei proposed in 2002 that close-in planets tend to be more massive. Close-in planets in binaries tend to be more massive than the general population. Now it turns out now, a few years later, because we now know 700 or something like that planets, and you drew a similar plot, and although it's confusing, the main point here to see is that the red and the blue points just overlap. I don't see any significant trend or major difference between those two, and that means that the planets in binaries seem to be exactly the same as the ones in single stars. So maybe it's not such a big difference. However, there is a caveat here, and that has to do with what is the actual mass of the planets, and I'll get back to that, irrespective of the period or the eccentricity, but what is the mass of the planet in binary systems, the distribution of masses for planets in binary systems. And this plot down here shows you, for all the systems, so this is like a couple of years old now, so I'm sure I could put some more points in here, but I know the trend is still there. For all the binaries that we know in which we found an exoplanet, at least one, you plot what is the mass of that planet, or the m sine I, because there's always a sine I uncertainty in there, as a function of the binary separation. And what you can see is that you have two different distributions. The wide binaries on the right of this plot, outside of 100 AU, have a very broad scatter that is exactly reminiscent of what you see around single stars. So as far as we can tell, the masses of these planets is exactly the same. But as you look at the closer binaries, within 100 AU, they all have high mass. And by high mass, I mean higher than typically a Jupiter mass. All right? And that is not a selection effect. There is no way selection effects can account for that. That is an actual fact. That is just an empirical fact. What do we make of it is uncertain, I guess, but that is where we stand. And as I briefly mentioned, this trend in planet mass doesn't show in any other parameters like the orbital period of the planet or the eccentricity of the planet or anything like that. It's only the mass of the planet that really makes a difference here. All right, so let me conclude by going back to the big picture and trying to put things together now as best as we can for now. Let's start with wide binaries. And by wide, I mean separations beyond 50 to 100 AU. These, as far as we can tell, have very little influence on the planet formation process. We found protoplanetary disks that are pretty normal. We found debris disks that are pretty normal. We found exoplanet mature systems that are very normal. So as far as we can tell, they don't make much of a difference. They do truncate, as illustrated in the cartoon here, but that's about it. And that's good news, because that means that almost half of these sort of type binaries are actually not making much of a difference for planet formation. Well, that's a good news if you want to see a lot of planets out there, of course. Depends what your goal is, I guess. Clearly, we have truncation. That has been shown in the protoplanetary disk. Only the inner 10, 20, 30 AU are preserved long enough to form planets. But obviously, that's enough. So long as you've been able to put enough mass into it at the beginning, you can form Jupiter-like, Jupiter mass planets or more if there is enough gas. Nothing prevents that. And it seems to go very much like normal systems. Now, if you look at closer binaries, now truncation gets much severe, of course. And now we start to see things being very different. Planet formation is not altered altogether. We do find planets in systems that are only 20 or 30 AU in separations, but they're not quite the same. First of all, many disks disappear very early on, or maybe even never formed at all, so that's obviously a problem. We do know that few debris disks form, so planetesimals are not formed as well or as frequently, and the planets that are formed eventually are different. They're always of high mass instead of being a broad distribution of very high to very low mass planets. So suggestion out of all of these differences is that the planet formation process goes through a different path in these type of closed binaries relative to wide binaries and single stars. Now, 3 years ago, when I was giving this talk in Rio, I was starting to talk about planets, circumbinary planets, and I was making the claim, there are some, but we'll never find them. Of course, I've been proven wrong. Kepler has came along and found already 3 of them, and presumably there are many, many out there, just a matter of geometry so that we can see them. So clearly, planets are fairly common in tight binaries. We don't have firm numbers to put on that fairly common statement, but they're not that rare altogether. If we found 3 already, there must be a lot of them. We do know that their protoplanetary disks offer very sound initial conditions. There are massive disks around circumbinary disks. And we do know that debris disks form very normally. So planetesimals will form very normally. So the claim here is that in these very tight binaries, where the disk is outside of the binary orbit now, the process is almost normal. I would say almost normal because the innermost region of the disk have to be perturbed by the presence of the stellar companion. It's not just the same thing as if you have 1 or 2 stars that are steering the pot in the middle. But as soon as you get a little bit further away, everything might just go the same process. And to put that conclusion into a visual perspective, I'll bring back the distribution of separations for all stellar companions to solar-type stars. Remember that broad distribution that peaks around 30 or 50 AU. And I will say, well, further out, outside of, say, 100 AU, we have a so-called normal process. And remember, I'm not talking about what is this normal process. That is not the scope of this talk here. Within an AU or so, you have the quasi-normal planets and process. That's what gives you to Tatooine-like systems. And in the middle, on the other hand, you get presumably a very different process that leads to a situation where you have 2 stars and 1 planet packed fairly close to one another, a la gamma set, which is the one illustrated here. And it is not impossible to form planets in these systems, but it has to go presumably through different physical processes. And these type of systems account for about 25% of all solar-type stars. That means 75% of all stars, solar-type stars, can form planets through a normal process. These other 25 probably go through a different process. I would argue something has to do with disk fragmentation, but we can discuss that in questions. So I'll stop here and take a few questions.
Gaspard, if I could kick off with the question about the high mass planets remaining around the close-in binaries. You sort of avoided the question of why that might be the case. Do we have any theories or speculation that you can throw at that?
Speculations, we can always speculate.
Yeah.
I don't think there are very good theories, or at least robustly demonstrated theories. I think you can, originally when I found that trend and when I published it, my argument was that in these tight binaries, we know we have very heavily truncated disks, so they're pretty compact. To form planets, to form Jovian-type planets, they have to be massive. And there is another companion right outside of it that is bringing some more tidal forces that might even further generate complex motions, let's say, inside the disk. And so my argument would be that those disks might very early on, as soon as the disk and stars are formed, fragment dynamically and go through a planet formation to the type that's advocated by Alan Boss of disk fragmentation. You have very compact, massive disk. It just can't cool, and so it has to fragment. And those processes typically lead you to high mass planets, Jovian type and higher. And so that might be, it might be that these planets that we see in tight binaries that are high mass are those that come from this process happening very early on, maybe even before we looked at them in Taurus or somewhere else. And the absence of low mass planets, on the other hand, might just mean that there's either not enough mass left in the residual disks, or they cannot live long enough, or the planetesimals that might form are just too stirred up by the presence of a companion to ever get to the point to actually form terrestrial Neptune-like planets that would not make it to the point of Jovian planets through core accretion, for instance.
Okay. Does the orientation of the rotation axes of the two stars affect the planetary development? Presumably, one can always assume they're collinear, but do binary stars always form with the same rotation direction?
As far as planet formation is concerned, I don't think we have a good answer to that question. That's too far down the road. You would expect binary stars to form with the two stars having the same spin axis. Naively, that's what you guess, because it's coming from the overall spin axis of the cloud in the first place. It is not true that they're always parallel, but they're generally roughly parallel. That's a fair statement. Now comes into the equation for planet formation the spin axis of a disk around the star. And now you have two stars, two spin axes, and a disk with a third spin axis. And that third spin axis doesn't even need to be, or doesn't have to be, parallel to its own star spin axis. So you get a lot of angles in there that you could look into. And part of the answer as to why we don't have any real knowledge that could address those questions is it's pretty difficult to measure spin axis for anything. For disks, it's pretty easy if you can image them. You can say, okay, it's oriented that way, the spin is there. But for the stars, it's relatively difficult, especially in the main sequence, for the stars that actually have formed planets. So we don't have, as far as I know, except maybe occasional one or two systems here and there where the information is available, we don't have a global picture. You would expect the relative orientation of the spins to make differences. My guess is that it more has to do with the spin axis. Oh yeah, I forgot the fourth spin axis is that of the binary, the orbital plane of the binary. Forgot, that's the most important one. My guess is that the two most important spin vectors are the one of the disk that will form planets and the one of the binary that's going around it. The spin axis of the stars in themselves is presumably not that important, or at least it would be a second or third order effect. So specifically as far as planet formation occurs, I don't have a good answer for that. I can tell you that people look into long-term stability of planets around in binary systems, and like the gamma sep system, 2AU the planet, 20AU the binary. So pretty close to one another. And there, the relative orientation of all these orbits is very important. And surprisingly enough, at least to me at the beginning, is so-called retrograde system, where a planet would go one way and this companion would go the other way, are actually more stable than systems where the spin vectors are parallel instead of anti-parallel. Reason being, when they're anti-parallel, they spend much less time close to one another. They're always, in other phases, or most of the time. So it ends up being potentially higher kicks, but much rarer. And so that ends up being long-term stable. So for the long-term stability of the formed planetary systems, it makes a difference. But we know too few systems that are at the extremes where it might be important. I mean, if the companion is 100 AU away, it doesn't really matter which way it's going. It's so slow that it doesn't make a big difference to the planet that's like an AU away from its own star. So I think we just don't know enough systems where we can have measured angles to address statistics there.
What was that system you mentioned?
Gamma Cepheids. Mm-hmm.
Hi. This also may be a little bit down the road kind of a question, but when, presumably, when the stars of a multi-stellar system form, and this question is mostly about the phase of protoplanetary disks, especially if they're different masses, one of them, I would think, would light up significantly before the second star lit up. In other words, maybe the bigger star would be a star, and the second star would still be a collection of gas, and maybe the bigger star's already forming a protoplanetary disk before the second star lights up. And I was wondering if anyone's done even any theoretical thoughts about what might happen to a protoplanetary disk when the companion lights up.
That's a good question. It is a fact that not everything happens neither in one go nor in a nice sequential process. That would be too easy. Things happen sort of like all at the same time, but there's always something that is going to happen first. The moment, I mean, even if you go back before even the protoplanetary disk phase and the sort of T-Tauri pre-main sequence star type phase, you have the protostellar phase and the pre-stellar core, which are much larger. And as those collapse because of rotation and angular momentum conservation, they're going to start to form something like a pseudo disk. It's not quite what we call eventually a protoplanetary disk, but something that is flattened, supported by rotation. And so disks appear immediately, essentially, is the outcome of that process. So people doing numerical hydrodynamical simulations of the process of a core or cloud collapsing to form stars, and generally find binaries in those, they do see disk appearing all the time. I don't think it makes a big difference the moment, as you say, the star is lit, because it's, first of all, a very gradual process. It's not like there's nothing and all of a sudden, boom, there's a bright star. There is something that's becoming more and more luminous as time goes, fair enough. And it's getting hotter and hotter as it contracts. But it's a pretty gradual process. And altogether, the luminosity that comes out is all coming from gravity until nuclear reaction start, which happens much further, much later than this phase. And so that energy is released continuously over time, just at different wavelengths. In the beginning, it's going to be in the far infrared or something like that. And by the time you get to the T-Tauri phase, you're in the near infrared, almost into the optical. But there is sort of a gradual process going there. I'm not sure that what really makes a difference for a disk, let's say, what make a difference, say, from the chemistry of the disk or the survival of the very smallest grains are the UV and the X-rays, the hard energy light. The infrared to far infrared just doesn't make a big difference altogether. It's just light and heat, but that's all it is. And the UV and X-rays, those will come more as flares type activities, magnetically related to magnetic activity of the stars, but those have to be already so-called mature T-Tauri stars. So there is a T-Tauri star in there. It's not a main sequence star, so there's no hydrogen burning yet, but it's already a pretty formed object with just contracting on the Hayashi tracks toward the main sequence. So then you could argue that, yes, sure, the presence of an extra source of extra UV and X-ray illuminating the whole thing in a different angle might make a difference. But that would be further down the road, a little further down the road than during the formation process itself.
Yeah, just comment on that. The protostars depend much less on stellar mass in terms of their luminosity than main sequence stars. So yes, there are some things having to do with angle, but in general, the nearby protostars will really dominate. There is an exception, though, and that is not when you're talking about the systems that you've shown, but when you have something like a B or O
Yeah.
star in the
I
system.
was going to get there. If you go to Orion, which has plenty of O stars, then you got all sorts of UV light, floated, and it can be even like a tenth of a parsec away or a parsec away, and it's still very substantial amount of light and high energy photons. So those might have very significant influence. But it's more the general environment at that point of where is that star formed? That is formed into a big OB cluster or in some sparser association like Taurus with essentially no N, O, or B stars, rather than being in a binary star.
Nowhere do I remember you saying anything about first generation versus second generation stars, but you talk about dust in the disk and things like that. I wouldn't think you would have much dust or solid matter in a first generation star. And do the same rules you've been talking about apply to both systems, or have you noticed a difference?
So all of these trends I've shown today are either pre-main sequence stars are forming essentially now, so they're second generation at least, you would say, and they're modern stars in a way, or nearby field stars. Those might have a few billion years of age, for some of them at least, for the lower mass objects, but they're still nowhere near the sort of metal-free kind of phase that happens in the very early universe. We don't have, by definition essentially, we have very few objects in the galaxy that are that old, that are very low metallicity. It's pretty rare to find objects with very low metallicity. There is a known trend that planets are found much, there is a very strong correlation between the metallicity of a star and the probability of having a planet. That's an established fact, that stars that are like the sun or having even more high, what we call metals, so the potential for having dust in the early phases, they have planets relatively easily. And stars that have less metals are much less prone to planet formation. That's an observational fact for the mature systems. We don't have any counterpart to that for the earlier phases like the debris disk or the protoplanetary disk phase, because by the time we see those objects, they're pretty young. Their debris disks are a few 100 million years, let's say, or tens of million years, and the T-Tauri stars are just a few million years, and those are born now, so they all have pretty heavy metals. So we don't have really empirical evidence. I'm not very familiar with the literature on theory as far as planet formation goes into low metallicity environments. I'm sure it makes a huge difference because of the absence of dust or much lower proportions. You would expect, but if you don't get rocky planets, you personally don't get Jovian planets either. You need a pretty big rocky body to form a Jovian planet in the first place. It's not going to happen just like that by putting gas together. You're going to get a brown dwarf out of that. That's different. So I would expect big differences, but I don't know the literature too well.
Hi,
Hans?
Gaspard. You talked about solar type stars and occasionally about slightly more massive A stars.
Mm-hmm.
But what about if you go in the other direction to the M stars, to the 0.5, 0.2 solar mass stars, which are interesting targets for transits?
Yep.
And so I wonder what the statistics is for those lower mass stars, and whether the same conclusions that you had for these solar type stars would hold for these lower mass host stars.
Right. So for the two Herschel surveys I've discussed, the debris survey goes from A to M stars. And we have about 90 of each of those spectral types. And the trend of lower frequency of debris disks in binaries holds across the board. It's, as I shown in the histogram before, the individual uncertainties are a little larger, but it seems to be the same everywhere. The difference in the separation and the fact that it's the intermediate separations that make a difference, if we put together the GK and M stars, because we need to for statistics purposes, it's still there. But there's not enough M stars that are binaries with a debris disk in the first place to make any statement just out of those. But I would argue, from what I see, I don't see any evidence that it depends on mass from A to M, spectral types. For protoplanetary disks, most of the surveys sort of gobble up all sorts of stars, say in Taurus. And as you know, you're going to get anything from almost a substellar regime all the way to a couple of solar masses. And there is no significant evidence that it makes a difference as far as the luminosity of the star is, therefore presumably its mass or its temperature if you want. So as far as I can see in gasps, the stellar mass is relatively unimportant and the main trends remain. The binaries just don't make any difference on that planet-forming region I was talking about. So as far as those two regions are concerned, definitely no trend, or no obvious trend at least. For the mature system, it's a little more difficult because not that many exoplanets are known around M stars in the first place. So again, you run out of statistics. to make very significant claims. And of course, around M stars, you don't get Jovian-type planets, but you don't get odd Jupiters, you get odd Neptunes or something like that. And so those would be in my forbidden region in that plot I showed of planet mass versus separation of the binary. But as it turns out, those are pretty rare. They're rare in the odd Jupiters around solar-type stars, as far as I understand. So it seems like those planets are also not that frequent. I guess a way to revise that plot once we know more planets would be to do the same with a ratio maybe of the mass of the planet versus the mass of the star, for instance. That would be more illuminative. But I haven't done that. And I don't think there are enough M stars with planets known in binaries. You need all these things together to get a good statistics out of.
Yeah, I was just noting as a comment that it seems like the Alpha Centauri system falls right in between your two red lines as a system that you would not expect to have any planets.
I don't recall the exact separation of Alpha Centauri on top of my head, but
it's like the exact separation is something like 30 to 40 AU. Yeah, and it's about 80-year orbit.
Yeah, so it is right down in the middle of that plot. I don't think planets. Like I said, planet formation is not inhibited there. It presumably go through a different process. Whether that process is equally effective in terms of how many stars we get a planet out of isn't clear to me, and I don't think there are yet enough statistics to really make a good statement there. Again, because you need stars that have planets and companions, and that's sort of like 10-20% here, 10-20% there. You multiply things together, you get pretty low fractions. So you need to survey many, many thousands of stars. So I don't think we can make a statement as to how frequently planets will form in such systems. My claim would be that they form through a different process, but they might still be there. We do know some systems. Gamma Sep, like I said, is 20 AU, and that's presumably the most extreme to date, but there are quite a few between 20 and 50 at this point.
Gaspard, there's obviously an amazing amount of stuff to delve into there, so if you have any more questions, please come up and talk to Gaspard after the talk. We have this object to hopefully increase the metallicity of your office.
There you go. Thank you very much.
Please join me in thanking Gaspard for his great talk.
Thanks a lot, guys.